So measures of central tendency are nice. That's the mean, the median, and the mode. But it's not the only important statistic. One that's probably more important is a measure of the dispersion or the spread of the data, right? So how spread out is the data? If we look at the frequency tables below that summarize the marks on test 1 and test 2, then we can see that which one looks to be a little more spread out.
The first one.
Yeah, the first one, right? Because in the second one, geez. I'm not coughing, I'm trying to clear my throat. In the first one, you'll notice that there are, like there's 7, 9s, and 10s here. There's 2 over here. There's 8, 14, 15s, and here there's 1. Right? So we have data that's more spread out. So we're going to use the stat function on the graphing calculator to find the mean of each set of marks. So I'm going to do it like this. So I'm going to go second, mem, that's not mem, second, mem, clear all lists, and get rid of this stuff, delete, clear all lists. Just a good habit to get into anytime you're going to enter anything into the list, right? We'll go to stat, edit. In L1, I'm going to put 9 through 15. Right, and double check. Yeah, okay, they're all good. In L2, I'm going to put the frequencies for test 1. So 4, 3, 7, 8, 4, 3, 7, 8, 6, 5, 3. And in L3, I'm going to put the frequencies for test 2. 1, 1, 8, 8, 7, and what are the last two? 0 and 1. Okay, I'm now going to go to stat, calc, one variable stats. Now, with the older firmware, then you need to tell it, so you say my x values are in L1, and then a comma, and my y values are in L2. If you've got the newer firmware, then you'll say list is L1 and the frequency is L2. Okay, and we hit enter. Now, what are we looking for a value for n? Right, we're looking for the total of this, right? So 7, 14, 22, 28, and 8, 36, right? So I'm looking for 36 for the n value, right? And there it is, n equals 36. That's a way to check back, did I enter the right thing? Because if you just run a one variable stats without entering anything, with the old firmware, you just go one var stats, hit enter, it'll just run it on L1. And you'll end up with the average of 9, 10, 11, 12, 13, 14, and 15, right? It'll only be like 5 things. Okay, so we want the mean of each set of data. The mean is 12. So test 1, 12. To do test 2, I'm going to go second enter, and instead of L2, I'm going to say L3, because I put my frequencies in L3, right? My observations are in L1. I have 2 sets of data, frequencies for test 1 in L2, frequencies for test 2 in L3. Hit this, we get 11.9 for the mean for test 2. Okay, so use the graphing calculator to draw the histogram marks using the window, 8.5, blah, 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 blah. Okay. So we're going to bring up the calculator. We're going to set the window. Window, 8.5. Okay, which is half a mark under the 9, right, under your lowest one, to 15.5, which is half a mark above. Okay, the width is 1. I want our bars to have a width of 1, right? So you'll see 1 for 9, 1 for 10, and so on. And for y, -1, just so it'll show the y-axis, or sorry, the x-axis, to 19 by 2s. Okay, now I got to go turn on stat plot, so plot 1. Okay, turn it on. The type is a histogram. Whoops, so I'm going to go over to a histogram, select that. My X list is L1. My frequencies for the first one, if I'm doing test 1, my frequencies are in L2. Okay, and then I hit graph, and we'll see the histogram for test 1. Okay, Now, let's do the histogram for test 2. So we just take a note. All right, yeah, that's what it looks like. So go to y equals, plot, same thing. But now I'm going to change my frequencies to be L3. Hit graph. And then we can see that distribution, right? So we have 2 different distributions. Okay, I don't know if I can do both together. Let's just try. Turn this plot on. And it's a histogram. And frequency will be L2. Yeah, it just gets kind of, it's hard to see which one's which, right? So not necessarily a good idea to do them both together. So we'll just turn off this stat plot. And graph. Okay, so we used the graphing calculator to draw the histogram. The means of the 2 tests are relatively close, 12 and 11.9, but it's apparent the marks for test 1s are widely dispersed, whereas the marks for test 2 are concentrated from 11 to 13. Right? We can see that in this histogram. Most of your stuff is here, and if we go back and just change this to be L2, you can see that it's pretty evenly spread out through the range of marks. Having a small spread or dispersion in test 2 may not be desirable, as it does not differentiate between the abilities of the students. By contrast, manufacturers of precision instruments want a small spread on the dimensions of items they produce. Either way, it's important to have a way of calculating a numerical measure of the spread or dispersion of the data. Most commonly used measures are the range, because range will just tell us the difference between the highest and the lowest, right? And that gives us an idea of, well, how spread out is the data, right? So we said if the marks ranged from 75 to 100, then that gives us some information. The marks ranged from 50 to 90, that gives us some information. The standard deviation, which is what we're going to look at now, it's a measure that indicates how the values differ from the mean, and the interquartile range, which is the difference between the upper quartile and the lower quartile, right? So we've got range, interquartile range, which we've looked at. Now let's take a look at standard deviation. Okay, and what does it mean? And not mean as in average, but mean as. Okay, determine the range of the following data: 56, 78, 80, blah, blah, blah. What's the range of the data? What are we going to write? Nope. What's the highest number? What's the lowest number? What's 81 minus 56? What's the range? 25. The range is a single number, right? We're not talking about the range as in the range of a function, right? Where we say, well, the y value is, 56 is less than or equal to y, which is less than or equal to 81. That's not what we mean by range in this particular case, right? We're talking data. Range is a single number. It's high minus low. Complete the following table for a sample of 10 data. All right. So we have x values of 12, 14, 16, 17, 18, 18, 19, 20, 21, and 25. We need the mean for that. How are we going to get the mean? Calculator, okay. So what do? Just add them all up? Do you need a calculator? I mean, really? Can't you just add them all up?
Yes. But it takes more time.
Does it? 26, 42, 363, 71, 81, 89, 99, 108, 118, 138, 139, 159, 164, 184.
We didn't have as much practice.
Okay. Well, I don't know. Do you agree or disagree? See, if you've done it on the calculator, which doesn't take any time, I got 184 adding them up. What do you get?
It's 180.
What is it?
180.
180.
Yeah, 180.
Is it? All right. Well, then I can't add. So maybe using the calculator would be a good idea.
Yeah.
Okay, how many are there?
10.
Okay, so is it 180? Yeah. Okay, so the mean is 180. So 180 divided by 10, which is, mean is 18. The sum is 180. Okay, we want the deviation, right? So we're saying, how far is 12 from the mean, right? So what's 12 minus 18? Negative 6. What's 14 minus 18? Yeah, okay, I'm pretty sure you can fill in the rest, right? maybe even correctly. Now, here's the thing, right? I mean, if we take these deviations, right, each one of these deviations tells us how far is this number from the mean. Now, the problem is if we just add them all up to say, well, what's the average difference from the mean? Stuff that's below will balance with stuff that's above, right? And that's not really saying what we want it to say. So we need to square these. So 36, 16, 4, 1, 0, 0, 1, 4, 9, and 49. And we need to add up the squares of the deviations. Let's try this again. 56, 57, 58, 62, 71.
71.
Yeah, 120. 120. Okay.
Oh, wait, we're going to add the last 49.
So they said determine the deviations from the mean. Check. Okay, so we did this. We got the mean. We got the deviations from the mean. We got the squares of deviations. The mean of the squared deviations. Okay, so we're not quite there. So how many of these are there? 10. So what's the mean of the squared deviations? Okay, so 120 divided by 10, which is 12. And what is the square root of the mean of the squared deviations? Root 12 is equal to 3.46. 4? So we'll go with 4.6. Go to the nearest 100. That's what's called the standard deviation. So the standard deviation is the mean of the squared deviations, right? The formula for standard deviation, you've seen summation notation, right? So the sum I equals 1 to n of x minus x bar, so difference between each individual observation and the mean, squared, right, which removes the negative, because if you just add them all up, you're going to end up with zeros, right? It just sort of balances on either side. That really won't tell you how spread out the data is. So we need to square them to get rid of this negative sign, and then we square root them to undo the squaring that we did. All right, so it's just kind of an interesting technique when you think about it. It's like, yeah, we got these negatives. We can't just add these together and then, you know, what if you add these together? What do you get? Like negative 13.
0.
And yeah, you get 0.
Oh, wow.
Right? So, you know, wow, what does that mean? Well, nothing, right? Yeah.
Nothing.
Deviation from the mean is nothing, right? So we square them to remove the sign, negative, and then we average them, and then we unsquare them, or square root, or whatever word you want to use for that. So, as you can see from the process, the standard deviation gives a measure as to how far the values deviate from the mean. A small standard deviation indicates that most values are close to the mean, and a large standard deviation indicates values more widely spread from the mean. When we talk about small or large, it's in relation to the actual numbers, right? We got numbers ranging from 12 to 25. So, you know, if your number's 12 and these numbers like, then that's huge. And if your number's like 0.07, then that's really small, right? And again, it depends on the data that you're actually looking at. The standard deviation of a population is denoted by, what letter is that?
5? 5.
No, that's the golden ratio.
It looks like 5.
It's not 5. It's sigma. It's a lowercase sigma.
Oh, they're
Look, uppercase sigma, lowercase sigma. And the standard deviation of a sample is denoted by S. And you will see them both on your calculator, right? I mean, actually, the way that we would do this is just to plug this into our calculator. Anybody put the numbers into the calculator? All these guys?
SX is...
Okay, and then you go 1 var stats, and you don't need to do anything else. So I assume you cleared your lists, right? And you get standard deviation is 3.46,
Yeah.
which is the sigma, right? The lowercase sigma,
Yeah.
not the SX. What's the SX?
3.65.
3.65. Yeah, it's calculated differently. Yes.
We do standard deviation in bio. I mean, bio we have n minus 1, not 10.
Yes, because there you use the sample standard deviation, which uses n minus 1.
Well, that's the population one.
And we do the population standard deviation, which uses, so, in IB, the formula, so you notice there's absolutely no difference here, right?
Except for one has U.
Oh, yeah, okay. Other than that, there's absolutely no difference here, right?
One uses sigma.
Yeah, so this, I believe, should be an n minus 1 for the
Yeah.
sample standard deviation. Okay? So, if you're doing this in bio or whatever, if you're doing this somewhere, I mean, look, you're never going to do these by hand, right? I mean, you've seen it, good, we'll leave it at that, right? Look, I saw it done by hand once. As a matter of fact, I even did it by hand once. But you're not going to do that for any reasonable set of data, right? And although they had to do that in the olden days before calculators, right? I mean, you either had, I remember there was a computer package called SPSS, which still actually exists. SPSS stands for Statistical Packages for the Social Sciences. And it runs any statistic you can imagine on a set of data. And it's still available today.
How good does it work?
It's still available today. That tells you some software that's been around, like, you know, what was the first spreadsheet?
1974.
What was the name of the first spreadsheet?
Green lights on
It's
the
called
left.
VisiCalc. How many of you have recently bought a copy of VisiCalc? Yeah. What was another big spreadsheet? You don't know this, right? Here, history of mathematics, computing. Lotus 1, 2, 3. Huge spreadsheet, right? When PCs first came out, this stuff started coming out. VisiCalc was actually written for the Apple IIe, right? It was done by a bunch of guys at Harvard who were doing an accounting course, right? And in accounting, in the old days with paper, you had paper ledger and you'd be filling numbers, and you made a change, you had to go in and change everything by hand, right? Re-adds, rows and columns and stuff like that. And they thought, hey, there's this computer out, maybe it can do it, right? So that's where the first spreadsheet started, right? Just somebody saw a need, hey, I'm doing this by hand, filled the need, right? And then it exploded from there. Then Lotus 1, 2, 3 came along, and they were huge, and now they don't exist anymore as a company. Now they're just VisiCalc. So what's the only spreadsheet you know about now? Excel, right? Word is not a spreadsheet. Unless you were saying Word as, you know, Excel, Word. Which would actually kind of fit, that'd be cute. If Brownlee was here. Okay, so we have population and sample standard deviation. Your calculator does both. I think as far as we're mostly concerned, as far as I'm concerned for us, it's always going to be the population standard deviation. If you go on, or when you go on, then you may be using sample standard deviations. And as Mohit said, in bio, you use sample standard deviations. Okay, the stat function on the calculator can be used to determine the standard deviation. So we did that, right? I mean, this is the same data.
No.
Isn't it? Oh, is that different?
No.
35. There's a 35.
Oh, there's a 35. Oh, well, okay, so then we gotta...
That changes everything.
It does, actually.
Yeah, a lot.
So I'm going to turn my plot off. It changes everything. Second mem, clear all lists.
Oh, that's a fact.
So what do we got? Edit.
I just spat and delete.
I'm going back to L1. If L1 ever disappears, and sometimes it does, and I don't know why, but it just does sometimes. Reset your calculator.
Well, second one, isn't it like? Yeah, second one. You did?
Maybe just press left on your arrows.
Oops. Actually, no, I'm going to leave that.
Why?
Because I'm going to run the stats on it. So stat, calc. If I'm just doing L1 on the non-firmware version of this, you can just hit enter. And I get a mean of 40, which is kind of weird considering that my lowest number is 35. Which should tell me that you might have messed up somewhere. Go back and look at your numbers again, right? So 12, 50. Now, I would say on any exam, anything that's for marks that you're doing this stuff on, oh, wait a second, that's 24. Anything for marks that you're doing this stuff on, always, always, always go back through the list, okay? Especially if it's numerical response. If it's multiple choice, the odds are pretty good that they will not put a distractor down that happens to be, what if they made a mistake and entered 245 instead of 24, right? You don't do that when you're writing multiple choice, right? You come up with other stuff. Like, what other numbers will they see in the calculator that we will do the SX, right? And they should be knowing that it's sigma x or something. So, but if it's numeric response, and you don't enter, like let's say I entered 25 instead of 24, there's no way that I would recognize from the numbers that I got, oh, I entered a number wrong. You know, here, saying, hey, the mean is bigger than the smallest, bigger than the largest number in your data set. Okay, you messed up.
The mean is bigger than the smallest number.
Okay, so stat, calc, 1 bar stats, and the standard deviation is 5.76, let's say. Okay, so sigma is 5.76. The stat function can also be used for grouped data. And in grouped data, so second mem, clear all lists, enter, stat, edit. So I'm going to need 14 through 18. Yeah, if you have numeric response and you're off by just one number, then your answer is just going to be wrong. You know, and then you get it back and you say, well, what did I do wrong? I'm pretty sure I followed the procedure. And I'm, well, okay, try it again. This time you'll come up with the right numbers because you won't know what mistake you made. And it'll be, so probably you entered one of the numbers incorrectly. So always check your lists, right? It only takes a moment just to go back through 4, 5, 8, 6, 2, yeah. And, you know, if they're longer lists, then just, I mean, you can see the whole list by going up there, right? And yeah, but you can't go through. So what I do is I look down here at this number. I don't look at the list there, so I just go 14, 15, 16, you know, okay, yeah, all those numbers are good. Go over there 2, I can go up the chart 2, 6, 8, 5, 4. All right, it's all good. You go to stat, calc, 1 var stats. On this calculator, you go L1, comma, L2. So what you're telling it is my numbers, my values are in L1 and the frequencies are in L2. And with the new firmware, you're telling it my values are in L1 and my frequencies are in L2. Only it actually prompts you for that. Okay, and we have 25. N is 25. That should be the sum of this, which it is, right? So that matches up. If you see like N is 5 here and a mean of 16, it means that you just did L1. All right, what did we want? Standard deviation, so that's 1.18. You know, to the nearest hundredth. I always like doing like nearest hundredth. You probably remember that we began this worksheet by examining the dispersion or spread of the marks for 2 tests, test 1 and test 1. Well, only we changed the other one to a 2. Find the range of the marks for test 1 and test 2 listed on the first page to compare the two values. What is the range of the marks for test 1?
A number.
And how do I calculate it?
Just 15 subtract. Yeah, this is just 15 subtract.
Okay, yeah, so the range is 6. What's the range for test 2?
Same thing, yeah.
Also 6. So range, as far as comparing those two tests, range is not going to be a good number, right? It doesn't distinguish anything between them. All right, they both went from 9 to 15. Even if one had gone from 8 to 14, you know, or 7 to 13, the range would tell us nothing other than there was a spread of 6 marks from high to low. Use stat function of graph calculator to find the standard deviation of the marks for test 1 and test 2 compare the two values. Note, always use standard deviation for a population. Note, always use standard deviation for a population. Okay, it's math, not science. Okay, so if I want to do this, I'm going to go second mem 4, clear all lists. Done. I'm going to go into stat. I'm going to enter edit. I'm going to edit. So the marks are what? 9 to 15, right? Sorry, what?
Let's
Go.
see after the video, it might pick up this.
4, 3, 7, 8, 6, 5, 3. 4, 3,
I did this for
3. And 1, 1, 8, 18. 1, 8, 18. 7, 0. All right, so I've entered these. I'm not going to bother checking because I figure enough of you will let me know if you have different answers, and then, you know, so I have a built-in check, which is you're also doing this, and we will figure it out. Okay, so stat, calc, 1 variable stats, and I'm going to do test 1 first, so I'm going L1, L2. And what do we want? Test 1, Morley force standard deviation, 1.73. And test 2, stat, calc, 1 var stats, L1, comma, L3. Okay, because that's where I put my frequencies. And we get 1.01. Examine the histograms for test 1 and test 2. Relate the shape of each graph to the size of the standard deviation. Okay, so we could just sketch those out, right? Turn this plot back on. It's already set as a histogram for L1, L2, so I'm just going to hit graph. And it's kind of I want two that are here. It's a little bit higher. Lower. I'm just, I'm just sketching it, right? So I'm going to do a sketch of it. I'm not windowing it and scaling it and all that good stuff. So stat plot, and this time we want L3. Graph, and it's like low, low, and then
It's not very slow there.
mid. Alright. Test 2. Okay, so really that's just a rough sketch of what we're looking at, okay? Now, how does this shape of the graph relate to the size of the standard deviation?
The smaller standard deviation, the more.
Smaller standard deviation,
Less spread out.
less spread out. Yeah. So what we have with the smaller standard deviation is we've got the data concentrated in the middle, right, close to the mean. With a larger standard deviation, we just have a larger spread. Okay? So larger standard deviation will give you a larger spread, or sorry, not really. A larger spread will give you a larger standard deviation, because standard deviation depends on the data, not the other way around. And the closer the data is to the mean, the smaller your standard deviation. Okay? That's a very interesting statistic you can look at. It's one that we look at when we look at like provincial diploma exam results, right? Because it tells us how spread out from the mean is the data. And as you move on in statistics, then you'll learn about the normal curve and stuff, and then relate that also to standard deviations. Okay, so question 9. Does the range or standard deviation give a better indication for the dispersion of the data?
Hey,
Is that even a legit answer?
That is a legit answer. It's just explained after you answer the question.
Yeah. Well, I think the answer to the first one is yes. No. Actually, I don't know if we can answer that one yet.
Standard
It's range or
deviation.
standard. Yes, one of them does. So standard deviation gives a better, right? Because the range said nothing, right? I mean, it's 6 and 6, while the range is the same. Okay. So does the range or standard deviation does? And now you explain that.
Okay, that was the old, so I said no.
Well, that's only true if they're both false.
They are both false.
Standard deviation. So what's the answer then? What's the better way, Grant?
The alien way that we haven't discovered yet.
Yeah, no, actually, we have discovered. Okay, so a smaller standard deviation tells us the data is closer to the mean, and obviously the corollary to that is that a larger standard deviation tells us the data is more spread out from the mean.
Can we write sigma so that and not just sigma?
I tend to just write sigmas, but I guess you could write sigma x. Or you write the sigma for what it is. So here we said sigma test 1 and sigma test 2. Like, I guess a lot depends on the context. If you're only figuring out the standard deviation for one thing, then you can just say sigma. But it's 3 histograms are shown below, A, B, and C. The graph with the largest standard deviation is A. The graph with the smallest standard deviation is B. The one with the standard deviation in between A and B, assuming the scales are the same, is C. Done.